Hi everyone, today's lesson is on arcs and central angles and also segment lengths in circles. So let's get started with a short review where we were talking about segments that are tangent to a circle at a point of tangency, which in this case, this is O. So if that's the case and that happens, then that means that this line right here is tangent to the circle R, and it's tangent meaning you're going to have a right angle right here because the radius that touches here at the point of tangency does make a right angle. So if OR is 6 root 5 and OT is 8 root 5, your job is to find the whole length RT. So we're going to use the Pythagorean theorem since this is a right triangle. And in doing that, we're going to start off with 6 root 5 quantity squared plus 8 root 5 quantity squared is equal to this length. I'm just going to call that whole length x squared. And so we know that 6 root 5 times 6 root 5, this is what we're really doing. 6 root 5 times 6 root 5. So that's 36. Numbers get multiplied with numbers. So 6 times 5, root 5 times root 5 is root 25, which is 5. 6 times 5. 6 times 5 is 30, 15, 16, 17, 18. So 6 root 5 times 6 root 5 is 180. So we have 180 plus, and this one's going to be 8 root 5 times 8 root 5, which is 8 times 8, which is 64, times root 5 times root 5, again, is root 25, which is 5. Multiply those around. We have 4 times 5 is 20. 6 times 5 is 30 plus 2 is 320. So we have 320 plus 180 is equal to x squared. If I add 320 plus 180, I get 500, and that equals x squared. I'm going to square root both sides, and in square rooting both sides, I'm going to get x is equal to the square root of 5 times the square root of 100, and the square root of 100 is 10. So we have 10 times root 5. Remember, the number 1 in front here gets multiplied by that 10. So x is equal to 10 root 5, which means that this whole length right here is 10 root 5. So RT is 10 root 5. Now, not only do they want that, but they actually also want ST, this little length here. So in order to find that, you don't have to do anything tricky, like I guess you can even make a proportion, but we're not going to do that. What you do know is that this radius is 6 root 5. So if this is 6 root 5 and that's 10 root 5, 10 root 5 minus 6 root 5 makes 4 root 5. So this little area right here is just 4 root 5. The next question talks about angle ORT. So ORT is 45 degrees. So this is 45 degrees here. RT, which is this length, is 10. Find OR. So they want this length right here, and then they also want this length, which is OT. Well, we know that this is a right angle because that line is tangent to my circle at the point of tangency, which is O, and that means that my radius, RO, is perpendicular, which means that this is a 45, 45, 90, which means x root 10. So that means that to find this length here, which is the same length as this, I'm going to set this equal to x root 2. So meaning I could go, because these are the same value here, x squared plus x squared is equal to 10 squared. We have 2x squared is equal to 100. We have x squared is equal to 50. Then we're going to square root both sides, and in square rooting both sides, we get x is equal to the square root of 25, 25 times 2, which turns out to be 5 root 2. So OT and OR are both 5 root 2. But there is shortcut to this. Remember, just setting this equal to x root 2 means I can go x root 2 is equal to 10. X is equal to 10 divided by square root of 2. In order to get rid of this denominator, root on the denominator, I'm going to multiply by 1, but in the form of root 2 over root 2. So I have 10 root 2 over 2. This 2 will cancel to 10 and make 5 root 2. So there's a couple of ways I can do that, but just know you can always fall back on the Pythagorean theorem. So the first part of the new topics are central angles. Now, a central angle is an angle that has its vertex at the center of the circle. So here's my center of the circle. So this is a central angle right here. So angle AOB. So angle AOB is a central angle, all right? And it means that if this angle right here is 50 degrees, this arc right here that goes from A to B is also 50 degrees. So not only is the measure of angle AOB equal to 50 degrees, but the arc, okay, the arc, which is a new word, we're going to talk about that, but the arc AB is also equal to 50 degrees. So let's talk about arcs. We have 3 different kinds of arcs that we cover in this class. The first arc is basically what we call a minor arc. And a minor arc is an arc that is less than 180 degrees. So, and we label it, let's say this is A and this is B, we would call that arc AB, okay? Any arc that's less than 180 degrees is what we call a minor arc. We have what's called major arcs, and those angles and those arcs are greater than 180 degrees. So that would mean something like if I had a value over here, let's say that's C, then I would go, this arc right here, ABC, would be a major arc. So that's arc ABC. Now, if I'm talking about a major arc, I'm going to use 3 letters. We have arc ABC, like that. That means that that's major. If I have 2 letters, that means it's a minor arc, okay? So any arc that's greater than 80 degrees is a major arc. Now, not only do major arcs use 3 letters, but we have another arc that's called a semicircle. And a semicircle, okay, goes through the center, because you've got to see that right there. There's your diameter. But your semicircle starts here, will go around all the way until the end of the diameter here to the other side of the circle. So let's call that D. So my semicircle would look like this, arc ABD, ABD, and that has a measurement of 180 degrees. So it's a semicircle. Arc ABD is a semicircle because the measurement for this is 180 degrees, okay? But you also could talk about this arc, which goes on this side. So you also could say arc ACD, the measure of that arc is equal to 180 degrees, and that's a semicircle. So just to recap, minor arcs are less than 180 degrees, okay? You would say a minor arc uses 2 letters. You could say minor arc AB, you could say minor arc BC, you could say, and BC would be from here to here. You could say minor arc AC, BC, you could say AC, okay? So those are all my minor arcs. You also have a major arc that's greater than 180 degrees, which means that you would start at one value point on the circle and go around. That which is greater than 180 degrees is what we call a major arc. And again, use 3 letters, that's a B. So we're going to go B, C, A. So B here, coming around, C, coming around A, B, C, A. And so that's a major arc. And a semicircle would be arc D, F, E. Okay, so we say that if you have a semicircle, you also use 3 letters. We're going to call that arc D, F, E. So minor arcs use endpoints to name so basically again, this arc right here is AB, but also central angle AOB. This major arc, we use 3 letters, semicircle, same thing, I just said that. Okay, so just basically a few things, how to measure an arc. When you find the measure of an arc, that measure of an arc is equal to less than 180 degrees. A major arc is greater than 180 degrees, and a semicircle is equal to 180 degrees. So we do have arc addition postulate. And this is formed by two adjacent arcs. Adjacent meaning next to, sharing the same point. So they see how these two arcs share point B. So these arcs are next to each other. We call those adjacent. So we could say that arc AB plus arc BC is equal to arc AC. And if this is a minor arc, we're still going to use two letters. It's very similar to the segment addition postulate that we did. Congruent arcs are two arcs that have the same measure. So AB, arc AB, and arc CD have the same measure. So if the arcs have the same measure, let's say they're both 50 degrees here and 50 degrees here, then therefore they're congruent because they have the same measure. One thing to note is that if this arc right here, my minor arc has a degree of 50, so does this here. That's my central angle. In the same circle, or in congruent circles, two minor arcs are congruent if their central angles are congruent. So basically what that means is up here, we were saying if the arcs are congruent, then the central angles are congruent. In this case, we're going to say if the central angles are congruent, then the major arcs are also congruent. In this example, it says circle P and circle Q are congruent. These two circles are congruent, and the reason why the two circles are congruent is because they have congruent radii. Do you see how these radii are both? That's 6, and so is that. Well, this radii right here is 4. So therefore, the circles aren't congruent. But they do try to trick you a little bit because even though my central angle, here's this arc is 80, that means my central angle is also 80, right? But even though my central angles could have the same measurement, that doesn't mean my circles are congruent. The only reason my circles are congruent is if they have congruent radii. So what we're going to do is we're going to look for two obtuse central angles. So two obtuse central angles would be this one right here, which would be angle XQY, and also this angle here, which is angle WQZ. Those are two central angles. Okay, in addition, we have a semicircle. We could say this right here, which is arc WXY, so we could say that. We could also say arc WZY, so we could say arc WZY. We also could say arc XYZ, so we also could say arc XYZ. So of course, there's a lot of answers for each of these problems, but we'll just cover some. For minor arcs, so a minor arc might be WX, XY, so arc XY, okay, arc WZ, so WZ, and maybe arc YZ, arc YZ. And then two major arcs, let's say I start with W, would be W, I'm going to go this way. So it'd be W, and I can either say X or Y. So I'm going to just say X and then Z. I could start here at X, and I could say X, Y, W. So I could say X, Y, W. And remember that I also could say X, Z, W. So that's the same thing. That arc is the same measure. That one is the same measure as the top one, but I just said them differently. So in this problem, it says find the measure of the indicated central angles, and the points shown are the centers of the circle. So if this is 100 degrees, we know this is 100 degrees because my central angle has the same arc measurement as this arc measure. So, and knowing that also that's a diameter, we know that's 100. So this is a straight line, which means that this plus this must equal 180. So that means X, the measure of X, that angle, is equal to 80 degrees. Okay, and likewise for this one, if I know that all the way around a circle is 360 degrees, and I know that from here to here is 240, and then I have another 60. 240 plus 60 is 300. So to find the leftover arc here, I just have to subtract, and I'm going to get 60 degrees. Now, keep in mind that this arc right here is also going to be 60, or that central angle right there is 60 degrees as well. So for this shape, for this problem right here, we have a circle, and we know that if all the way around the circle is 360 degrees, again, we have 75 plus 50 is 125. So we know that from here to here is 125. We then know that the rest of this, okay, we're going to subtract 125 degrees, all right? So we have 235 degrees. So we know that from here all the way around to here is 235 degrees. So that's actually arc GHE. So GHE is 235 degrees. Then we are looking for EHF. So that goes from here and goes all the way around to here, okay? Which means basically that this being going all the way around is 360 degrees minus 50. So 360 degrees subtract 50 degrees is 310 degrees. So this one would be 310. GQF, so this major arc here has a measure of 75 degrees. EQF would have a measure of 50 degrees, central angle. GQE, so this length here, which is 75 plus 50, is 125 degrees. And arc GE would also have the same arc measure as this. That's the central angle as 125. For this problem right here, they're showing two concentric circles, all right? The N is the center. Classify each statement as true or false. So the measurement of arc BC is 45. So BC is 45. Would this be 45? Well, we know this is right. This is right. Therefore, if this right here is 45, that has to be 45, correct? That's true. AB, so arc AB and arc VW. Now, we know the central angles are both 45 degrees, but that doesn't mean the arc measure is the same. So we know that this congruent, this arc is not congruent to this because they're not the same length. But we do know that the central angles are both the same. So they both have the same central angle, but the lengths of the arcs are not the same. So that's not true. D and C, so we have D and C is 90 degrees, the measure of that angle. That's a true. Arc XY, this arc right here, is equal to 45 degrees. True or false? This right here, this arc right here is equal not to 45 degrees. False. VW, so we have VW is equal to VX or WX. True. And then we have AED, so arc AED, so this arc right here is congruent to VZY. The arcs are not congruent. The central angles are congruent, but our arc measures are not. So what we have is if checking your answers, you can check them. On this problem right here, we have problem, this is from our homework. The hands of a clock form 120 degree angle. So what I want you to think about is this being 12 o'clock, okay? Over here is 3, and we know that this is 1, 2, 3. We also know that this is 90 degrees here, okay? So if this is 90 degrees, that means I'm dividing 90 by 3, which means that each one of these hands is 30 degrees. So we've got 30 degrees, okay, each time. So I want a 120 degree angle, so 30, 60, 90, 120. So there's a whole bunch of ways that I could draw my clock. So that would be at the 12 and at the 4. I mean, I could draw it all the way. I could take that arc and like twist it all the way around. Now we're going to talk about lengths of segments in circles. So we have something called the chord length theorem. It means that when you have two chords in a circle, the product of the lengths of the one chord equals the product of the lengths of the other chord. So that means that this segment right here, ST, that segment, times this portion of that segment, TR, is going to equal QT times PT. Okay, so this length times this length is going to equal this length times this length. Okay, that's what it means. So if this was 5 and this is X and this was 3 and this was 10, we would go 5 times X. So you'd say 5 times X equals 3 times 10. So 3 times 10. So you have 5X is equal to 30. So X equals 6. This is just the chord length theorem. Again, this length right here times this length is equal to PT times QT. So solving for X, we can say 4 times X. So we'd go 4 times X equals 3 times 8. So we have 4X is equal to 24 divided by 4. X equals 6. Okay. Our next theorem is a secant length theorem. If you notice, we have two secants. So we have secant DF and we have secant HF. So both of these here, you've got EF is an external part of the segment, and this is GF external. Basically, the formula says that if you have the outside times the sum, so basically EF times the sum, which would be DE plus EF, and I'm just going to call that DF, is equal to the outside here, FG, times the sum, which is HF. So you've got the outside times the whole segment is equal to the outside times the whole segment. Okay, so let's do one of those. That's the formula again. So in doing one, I'm just going to call this, let's see, X, 5, 7, and 3. And so what it would be is the outside, so 5, times the sum here, which is X plus 5, is equal to the outside 3 times the sum, which is 7 plus 3, which is 10. So we have distribute, we've got 5X plus 25 is equal to 30. I have 5X equals 5. X equals 1. Okay, so that would be my length of X. So another problem, again, outside, so we have 5 times the sum, which is 8, equals the outside X times the sum, which is X plus 6. And so we have 40 is equal to X times X, which is X squared, X times 6, which is plus 6X. I notice this is quadratic, so we're going to set that equal to 0. We have X squared plus 6X minus 40 is equal to 0. I could use Pythagorean theorem, I could use the quadratic formula, or I could factor. In this problem, I'm just going to factor, and I'm going to ask myself, what are my factors of 40? So my factors of 40 would be maybe 1 times 40, 2 times 20, 4 times 10, 5 times 8. Which one of these is going to give me 6, a sum of 6, if this is a minus? So I know that one of these is plus and minus to make negative here. We know this is X times X, which is going to give us X squared. But which one of these is going to add up to be 6? Since I don't have a value in front of my X, I don't have to worry about that. So it's going to be this one. And I notice it's a positive 6. So that means that this is going to be a positive 10 and a minus 4. So we're going to split this up. We go X minus 4 is equal to 0. We get X is equal to 4. We go X plus 10 equals 0. So X is equal to negative 10. In this problem, you're not going to have a negative length. So that eliminates that possibility. So my answer is going to be x equals 4. Now, please keep in mind that we did get negative 10 as an answer, but it didn't work as a solution. So what we do is we write it like this so that negative 10 is what we call an extraneous solution, which basically is a solution that you get, but it doesn't work when you plug it back in. The last theorem that we have is the tangent squared theorem, which basically means if you have a line that's tangent and a secant, okay? So blank is tangent, so we have line segment AP is tangent. We have PC, which is secant, and an external part of the segment, which is PB, all right? So what we have here is that the formula says that this length here times itself. So we have AP times AP, which we call AP squared. Okay, use parentheses, is equal to, again, the outside PB times the whole length PC. Okay, that's what it says. So just writing it again, AP times AP, which again is AP quantity squared, is equal to PC, the whole length, so PC times PB. And just keep in mind, multiplication is commutative, so I could say PB times PC instead. So let's do one like that or more. What we have is a few to review the theorems. So again, these are the 3 different ones that we just talked about. This theorem says ST times TR. So this length times this length is equal to QT times PT. This one says the outside EF times the sum, which is FD, is equal to the outside FG times the sum, which is FH. This last one that we just talked about says AP, so we have AP squared. So AP times AP is equal to the whole length, PC, times the outside segment, which is PB. Okay? So practicing these to find x. Now, for these problems that we're going to be doing, it might be a good idea just to start and stop the video as you go so you can try these ones on your own. So this would be a good time to start. So for this problem, we're going to go x times 6. So that's our theorem. So we're going to go x times 6 is equal to 2 root 2 times 4 root 2. All right, so we have 6x is equal to, and remember, numbers get multiplied with numbers. So 2 times 4 is 8, and roots get multiplied with roots. So root 2 times root 2 is root 4, which is 2. So we have 6x equals 16. I'm going to divide both sides by 6. I get x is equal to, now let's divide into 6 with 2. So dividing 2 into 6, we get 3, and this 2 will cancel. So what I have is 8/3. So my answer for x is 8/3. Next problem, again, you've got the outside times the sum. So we have 3 times 8 is equal to the outside x times the sum, 2x plus 1x, which makes 3x. So we have 24 is equal to 3x squared. So we're going to divide by 3, I get 8. 8 equals x squared. I'm going to square root both sides. And that's just the square root of 4 times the square root of 2 is equal to x. And so that's 2 root 2. Remember, when you do take the square root of something, you do get plus or minus, right? But knowing that you can't have a negative length, that negative is just not even considered. So this one, and this is our first example of doing one of these, again, is 20 times itself. So it's 20 times 20 is equal to the outside, which is 2x, times the sum. So 3x plus 2x, which is 5x. So 20 times 20 is 400, is equal to, numbers get multiplied with numbers. So we have 10, x times x is x squared. So we have x squared is equal to, I'm going to divide by 10, I get 40. I'm going to square root both sides, and I get x is equal to the square root of 40, which is going to be root 4 times root 10. Square root of 4 is 2, so my answer 2 root 10 for x. Plus or minus, again, no negatives are considered. We have 2 more problems down here. Find x. So practicing this one, this is going to be 3 times x is equal to 6 times 4. I'm going to divide by 3 on both sides. I get x is equal to 3 goes into 6 twice. 2 times 4 is 8. Again, x times itself. So we have x squared is equal to the outside 8 times the sum 20. So we have x squared is equal to 160. X is equal to the square root of 160, which let's reduce and let's make that root 16 times root 10. Square root of 16 is 4, so this will be 4 root 10. 2 more. This one is, let's see, 4 times this, which is x. So 4 times x equals 8 times that value, which is not there. But because we know that this comes down and is perpendicular, that means that this is bisected, so that's 8. So 8 times 8. And then we have to divide by 4 on both sides, and we get x equals 4 divides into 8 twice. 2 times 8 is 16. For this problem right here, we have outside. So we've got x times x, which is x squared, is equal to the outside times the sum, which is 18. So x equals the square root of 8 times 18. I'm not going to multiply those out just to reduce them again. So I'm just going to reduce these in my roots. So we have x equals, let's see, 8 is going to be 4 times 2. Thinking perfect squares, 18 will be 9 times 2. Square root of 4 is 2. Square root of 9 is 3. Root 2 times root 2 is root 4, which is 2. So what I have is 2 times 3, which is 6. 6 times 2, which is 12. So I've got x is equal to 12, which basically means that had I multiplied these two numbers together, I would have, in fact, gotten 144, square root of 144, which I could have just square rooted that and gotten 12 anyways. Last one, let's do this. Outside x, so we go x times the sum of the lengths is going to be 3x is equal to the so outside times the sum is equal to 12 times 12, which is 12 squared. This looks like I have 3x squared is equal to 12 times 12. I know that's 144, but I'm just going to divide by 3 first, because what that's going to do is change this to a 4. And now I have 4 times 12, which is 48, of course. But I mean, realistically, is it any good to get root 48 like this and then divide it again by 4 times 12? Well, technically, yes, because at this point, I could have said, well, that's root 16 times root 3, and therefore my answer is 4 root 3. But because this is math and we have so many different ways to do these problems, I'm just going to continue doing this. And I've got 4 times 12. Square root of 12 is 4 times 3. So we have square root of 4 is 2. Square root of 4 is 2. Square root of 3 is root 3. So we have 4 root 3. So, like I said, there's so many different ways to do these problems. Pick one way that you like and stick with it. So that's day 2, which was arcs and central angles and also circle segments. So thanks for watching.